We're on to chapter 3, and chapter 3 is really just an application section. At the end of chapter 1, they had an application where they set up differential equations. And in chapter 2, we learned how to solve some differential equations. First order differential equations. We solved some linear ones and nonlinear ones, separable. We found that some of them are homogeneous or Bernoulli types. And so we have a good amount of arsenal now to be able to solve a handful of differential equations. And so they had chapter 3 to be this idea of being able to solve differential equations. So here's the beginning parts where they're all involving exponential functions, the results are. And the growth and decay and Newton's law of cooling are two examples where we were able to solve for these things using separable differential equations. These, by the way, are autonomous, also autonomous differential equations, right? The slope is equal to something with just the dependent variable involved. And there's going to be a handful more of formulas that they have here that we can use, that we come up with. And so when you're dealing with mixtures, or when you're dealing with circuits, or dealing with springs and stuff, so a lot of them have formulas associated with them, so we don't have to kind of reinvent the idea of what we did at the end of chapter 1. So my plan today was just to take a look at some of the homework problems in section 3 or chapter 3 and see if we can try to tackle a couple of them and give you kind of a head start on your homework. So let's do that. So this is chapter 3, section 1. The dead body problem is always interesting. Kind of makes the, those CSI shows and stuff. You can, yeah. You can, you can pretend that you're able to solve for this using differential equations. They now have ways to calculate this a lot quicker, but it's all originally based on differential equations. So let's see if we can solve for this problem. A body was found within a closed room of a house where the temperature was a constant 65 degrees. So there's some parameters there that are important for us to be able to use this simple modeling method. Otherwise, it gets a little bit more complicated, or a lot more complicated. But we had the ambient temperature to be 65 at the home. At the time of discovery, the core temperature of the body was determined to be 85 degrees. And then an hour later, a second measurement showed the core temperature was 80. And so assume the time of death corresponds to T is equal to 0, and the core temperature at that time was our usual 98.6 degrees. Determine how many hours elapsed before the body was found. So, they walk in and somebody looks at the body and says, oh yeah, the time of death is blah, blah, blah. So this is how they would compute it. So it says, hint, let T1 be bigger than 0, denote the time the body was discovered. All right. So let's see if we can come up with some important information here. First, the differential equation involved here is Newton's law of cooling. This is a body temperature that's going down and it's going to hit the ambient temperature, and we just kind of wrote that down in the previous page. So it's some constant times T minus T sub m, the ambient temperature. So if we just take a look at this information, this is going to get us what we need. So let's fill in some of the things, some of the parameters that are involved here, like the constant temperature of 65 degrees. What do you think that corresponds to in our Tm is 65 degrees Fahrenheit. Our T0 is equal to T naught, where T naught is the initial. What's that equal to? It's 98.6. Is there anything else? So the body was discovered at T sub 1. Which is going to be our base time, and then from there we need to figure out, going backwards and forwards, figure out when the time of death was. So T sub 1 is when it was discovered, and what is the temperature of the body when it was discovered? 85 degrees. And so at some time later, the temperature was taken again, and so it'll be T sub 1 plus an hour later. The temperature was taken again, and that was 80 degrees. So this is your setup information, and this will help us solve for the differential equation. So I'm assuming we're eventually going to want to solve for T sub 1 here. It'll give us the time of death. Okay, well, let's put in what we got. dt. I suppose that's not a good choice of variables here. T minus 65. So this is your differential equation, and we can actually go through the process of solving for this differential equation, or we can just try to remember what it was. I don't remember. Plus something. I don't quite remember what it was, so let's go through the process of solving for this. So these two pieces of information, by the way, the two different temperature times, that's not 0, that's not the initial. These two temperature times will help us determine our K constant. So before we do that, we need to find our original function. So let's do the differential equation. So T is going to be equal to A e to the kt. Are you telling me because you know, or? I don't either. That's why I was going to redo the whole thing. All right, well, it's good practice anyways. This is a separable differential equation, so let's solve for it separately. The capital T over T minus 65 is equal to K dt. And then take the integral of both sides. We're going to get an ln of something on one side. Is equal to kt plus constant. And then you take the exponential. So yeah, it was just the same thing, like you said, plus 65. So T minus 65 is equal to e to the kt plus c. and that's going to become the A constant. And then, so t is going to equal to the e to the c will become a being multiplied there, kt, and then add 65 to both sides, and then you get your value. And what we'll do is we'll use the initial condition, which is 98.6 when t is equal to 0. So initial conditions, IC 98.6 is equal to a e to the k times 0 plus 65, so that a is equal to 33.6. So our function without the t yet, or without the k yet, is going to be 33.6 e to the kt plus 65. All right. So we're almost there. Now we're going to plug in those two values and hopefully be able to solve for t sub 1. So we'll use these other conditions. We have capital T of t sub 1 is equal to 33.6 e to the k times t sub 1. T sub 1 is an actual time now. This is when the body was discovered. Plus 65, and then we'll put capital T, t sub 1 plus 1 is equal to 33.6 e to the k t sub 1 plus 1 plus 65. Oh, and this is supposed to be equal to 80, and then the first one, which I forgot to put, was supposed to be equal to 85. So we have two equations, and we have two unknowns, k and t1, and we should try to solve for them. I don't know what the best way to solve for this is. Normally I'd probably just solve for k or t on one of them and then plug it into the other one. I don't know if there's an easier way to do this. That's probably so let's take the first one, and we're interested in finding t sub 1. So if I solve for k in the first one and I put that k into the second one, then it'll be in terms of t plus 1. So let's solve for k here. So this would be, bring the 65 over to the other side, divide by 336, take the ln. All right, too many steps. So k is equal to 1 over t sub 1 ln of 85 minus 65 divided by 33.6. Boy, is that right? So bring this 65 over to the other side. That's 20. Divide by 33.6. Take the ln of both sides. And then divide by t sub 1. Okay. So now I'll take that k and put it over here. Are the t sub 1's going to cancel? What? Well, that's no good. Oh, thank you. Okay, good. So now, if we do that, we got 33.6 e to the k, that's 1 over t sub 1 ln of, that's probably going to be, this is 20 over 33, so this is going to be a negative number. Plus 65 is equal to 80. I'm just going to divide or subtract 65 from both sides. Is that going to be 15? All right, let's start peeling away here. I'm going to divide out by 33.6. And then we could take the ln of both sides again like we did before. Suppose somebody can try to figure out what 22 over 33.6 is if they want. Now, try to make it cleaner by just dividing out by the ln. This is 20. So if I divide both sides by ln, and then this becomes 1 plus 1 over t sub 1. Then I have to add 1 and take the reciprocal. Well, you guys can do this on the calculator, right? So 15 over 33.6, I'm still carrying these uncomputed values. The top one? Yeah. Good watching out, guys. And then figure out what this number is and take the reciprocal. So, did anybody do that? I think this is the 1 over t times this times that. So I divided this out, and then I multiplied, I distributed 1 over t sub 1 times t sub 1 is 1. 1 over t sub 1 times 1 is 1 over t sub 1. Okay. Too bad I closed down MATLAB, huh? So, did you guys get a solution for this? So it's the reciprocal of this big mess. Suppose I can type that in and see if I'll get the correct answer. Oh, enter a number. Can't enter an expression. So, punch that in. All right, let's see what happens. All right, looks like it worked. So it's just a big algebra mess, intermediate algebra, or sometimes it's seen in pre-calculus, but it's just a bunch of logarithms and exponential functions and solving for variables. You know, the real calculus part is up here, and the real differential equations part really was before that, identifying that it's actually a separable differential equation. That's really the only new DE part. Everything else was calculus, and then from there it became algebra. I mean, it was tedious algebra, but it's still nevertheless just algebra. So just be careful when you're working that out. Okay? All right, let's do another one. Which one should we do? There's one on circuits. Series circuits. I don't know. Let's do should we do 5 or 6? So number 6 is going to require us to do 2 problems, I think. Let's see if we could do this. So electrical force is given by that, and so for a certain domain, time from 0 to 30, it's giving an electromotive force, and after that it goes to 0. So it looks like there's going to be 2 differential equations that we're going to want to work with here, and then fill in your current. So the function that we probably will need is one of these 2 things. So for current, the sum of voltage drop across the resistors is this, and capacitance is given by Q of T over C if we had a capacitor. So it doesn't have that, so I think it's just the first equation is what we're dealing with. Yeah? Have you guys taken circuits? One person? You guys eventually have to take circuits? Yeah. All right, so here's your differential equation that we're dealing with. What's L? Okay, so it says here in a circuit in which the inductance is 30 Henry's and resistance is 3 ohms. So what's L? It's what? It's so the R would be the resistance, and what's the L stand for? Conductance or inductance. So that's the Henrys. And so all we have to do is have a different E for the different domains. So we'll do this differential equation problem twice, and your function is I. It's I of t. Sometimes people use capital I because little I looks a lot like the imaginary number. And then we'll redo the same problem. Probably won't have to redo the whole thing in so much detail because we would have gone through the procedure of solving for the other one. Okay, so the first step to make it look like how it's supposed to look like is to probably divide by something, by 30. We could, but I think we want to set this up like it was a linear differential equation. So this is where you would get a 1/10. Is this 70? 7, right? And so this is actually we can look at it as a linear. It's a separable differential equation, but since it's already looking like it's a linear differential equation, let's approach it that way. And we find the integrating factor. Remember how to find the integrating factor? So e to the integral of, this is just a constant. And so that's e to the 1/10 t, or t over 10. And since we're all experts on this already, you can just skip a couple of steps where it looks like a product, and then you unravel it and put it together as a product from a product rule. And you get that by multiplying both sides of your equation by the integrating factor. So then all you have to do is integrate both sides. And you're eventually solving for I. So let's call this e to the negative t over 10 moved over to the other side. The antiderivative of this is fairly simple, right? Is it simple? It's like 70 e to the t over 10 plus c. It's a constant, so we don't have to do any fancy integration by parts. Just take the 7 out. Antiderivative of e to the t over 10 is e to the t over 10 divided by 1/10 or something like that. I don't know. Is that right? So there's a plus c from the integral, and then I took the e to the t over 10 over to the other side, so that's why there's a negative power there. And we'll use I of 0 is equal to 0 as the initial condition. So when we put 0 in, this would just be 1, 70 times 1 plus c, and so that'll help us find c. C is equal to negative 70. So I is equal to e to the minus t over 10, 70 e to the t over 10 plus minus 70. And I suppose you can rewrite it, and if you're taking a circuits class, they won't go through all this differential equation steps. They'll just come out with the answer. And if you come out with the answer, they most likely be factoring out a 70. And so if you just switch this around, 70, and this would be 1 minus e to the negative t over 10. So now imagine doing the same thing on the other side, except instead of a 7 you get a 0, which is going to make things a lot nicer for us, I think.
Isn't that negative e to the negative t over 10
Oh, because this is a negative, this is a positive, and if you add the exponents, it's like e to the 0. I hope that's right. So if you copy through the same things, except this is 0. So if you imagine this is 0, the antiderivative of this is just a constant. So all this stuff would be gone. And then all you would have is 70 times e to the negative t over 10. So I'll let you do that. Let me check the answer for the first one. 71 minus e to the negative t divided by 10. Got really small there. I don't know if this is a plus or a minus. We'll see. Oh, just 0? Would it just be 0? The whole thing 0? Right. So, should we try 0? Well, actually, you guys can try to figure it out. Just put in 0. This is what you guys do? Just put in 0 and see what happens. Well, you guys can figure this out. Again, go through the same process, except instead of a 7, put a 0 in there. Go through the antiderivative, which will give you a constant. Antiderivative of 0 is a constant because the derivative of constant is 0. So you can check that and then go through the process and put in your initial conditions and see what you get. Okay, that was interesting. So the next section so there's a few more applications you could take a look at and see how you feel about it. The next section extends to nonlinear models, but it's still stuff that we should be able to solve for. Examples are like the Bernoulli and the homogeneous differential equations. We ran into a couple of those that are nonlinear, and then also if it's a separable differential equations, then it's really easy to deal with. So those are also falling under the category of nonlinear differential equations, and they're all first order. All right? So this should be enough to get you going in your homework, and then on Thursday we'll review. The quiz is due at 11:55 tonight, online, so get that done. All right, see you guys on Thursday.